I'd like to transition now to talk a little bit about real gases. So we've seen that real gases violate some of these key assumptions of the kinetic molecular theory, and to a larger or smaller degree, they violate the ideal gas law as a result. So as a starting point for thinking about real gases, let's start with an assumption that all gases, by definition, violate. All gas particles do, in fact, experience intermolecular forces and do take up some volume. There are two important implications for this. The first is that in a real gas, the volume that's actually accessible to particles is not the entire container volume, but the container volume minus the volume taken up by all other particles. Right? Particles can't move through each other and they can't sit in the same spot, and so the real volume is less than the ideal volume, since not all of the volume of the container is accessible to all gas particles. Secondly, if we assume that gas particles attract one another, as they typically do, intermolecular forces are typically attractive, the real pressure is lower than the ideal pressure, since collisions of the particles with the walls are weaker than they would be in the ideal case. And this can be a little bit non-intuitive, so I want to draw a little picture to help us understand this. We think about a gas, there are many particles in the middle of the gas, but the ones that are colliding with the walls are the particles that are on the periphery, which I'll draw here in red. Now these peripheral particles, because they're on the way to collide with the wall, they don't really have any other gas particles on, say, the other side of them. There may not be any particles between them and the wall. What that means is, in terms of intermolecular forces, they're experiencing force behind them, and if it's attractive, they're being pulled to some degree back towards the center of the container. Now, this effect may be minuscule if the intermolecular forces are small, but it can be large if the intermolecular forces are significant and strong. This pulling back towards the center of the container slows these molecules down that are about to collide with the walls of the container, and lowers the observed real pressure relative to what the ideal pressure would be if there weren't these pulling back interactions between the gas particles. Van der Waals was one of the first people to notice this, and he altered the ideal gas law based on these two ideas, using variables A for a pressure correction and B for a volume correction. You'll recall that in a previous video we alluded to the fact that real gas laws bring in parameters that depend on molecular structure and that differ for different gases with different molecular structures. And this is our first example of that. A and B depend on the specific identity of the gas in question. So here's Van der Waals' real gas law. And although it looks a little bit cryptic, it's actually not terribly difficult to understand what's going on. So A is the pressure correction. Van der Waals reasoned that the pressure correction is going to be inversely proportional to the volume. It'll be more significant for a smaller volume, right? Since these pulling back interactions are going to be stronger and more important at a smaller volume. And they're going to depend on the strength of the intermolecular forces, which is basically where this parameter A comes in. B is the volume correction. We subtract B from the volume to account for the volume taken up by the gas particles. So these two correction factors, A and B, take into account these two, you might say, limitations, these two properties of real gases. And the nRT, of course, is the theoretical or the ideal pressure times the volume. Another way to think about real gases is to think about what's called the compressibility factor Z. If we think about a mole of gas, according to the ideal gas law, at all pressures, all volumes, and all temperatures, the ratio of the product of pressure and volume to the gas constant times temperature should be equal to 1, right? And this ratio is known as the compressibility factor. Z is in general not equal to 1, in fact, and studying how Z depends on pressure, temperature, and the identity of the gas helps us see when gases tend to act most ideal. In other words, at what temperatures, at what pressures, and what molecular structure characteristics lead to ideal behavior or not to ideal behavior. So we're going to look for molecular level explanations for the trends we observe in Z. So here's a graph of the compressibility factor versus pressure and temperature for a wide variety of different gases. So what exactly are we seeing here? Well, on the x-axis, you're seeing the reduced pressure, which is just a pressure measure relative to some standard. And on the y-axis, we have the compressibility factor. The different curves are for different gases at different temperatures. So different gases are the different points on the curve, and the different temperatures are the different lines. And we start at low temperature, TR equals 1.00, and move up to higher temperature, TR equals 2.00. And again, this is just a reduced temperature relative to some standard. So what are some of the trends we noticed here? Where are gases most ideal? One of the first things to notice is that the compressibility factor is almost universally below 1, at least within this regime of temperatures and pressures we're looking at. It gets most ideal at high temperatures. TR equals 2.00. All of the gases are sort of living up near the 1.0 line. They're not quite there, but they're in the range. As we go to lower temperatures, gases get less and less ideal as a whole. You'll notice a huge smorgasbord of gases behaving non-ideally right there around 1.0 in reduced pressure at TR equals 1.00 near the very bottom of all the different curves. In terms of pressure, we notice ideal behavior first of all at very low pressures and then apparently again at very high pressures. So at very, very low pressures, notice that all the lines are converging on 1.0. All the lines are converging on a compressibility factor of 1. And as we move up to higher pressures, we're approaching 1 again. In fact, if we continue going, the compressibility factor gets even higher than 1. So the most general takeaway from this is that as pressure decreases, gases become more and more ideal. So let's think about this for a second. What are the likely molecular level or microscopic explanations for the trends in compressibility factor versus pressure and temperature that we're seeing here? It's worth keeping in mind that really the essence of violations of the ideal gas law come down to interparticle forces within an ideal gas. And where we see the most ideal behavior is where intermolecular or interparticle forces are least important. We've noticed two situations where gases behave quite ideally: high temperature and low pressure. Why do these two situations lead to ideal behavior? Well, let's start with high temperature. When a gas has high temperature, that means its particles are moving very quickly. And one way to think about that is that the kinetic energy of the molecules is very, very large. It's very large in comparison, for example, to any sort of potential energy the molecules might have due to intermolecular forces. And so the behavior of the gas is going to be dominated by its kinetic energy. This is sometimes imagined as the particles zipping past each other very quickly with very little time to engage in intermolecular forces with one another. And that's, I think, a nice qualitative explanation of what's going on here. The kinetic energy of the particles is so large in a high temperature gas that the energies of intermolecular forces is essentially irrelevant. That's why high temperature gases tend to behave ideally. What about low pressure gases? Well, let's think about how we achieve low pressure within a gas. The way to achieve low pressure within a gas is either to raise the volume of a gas to a very high level or remove particles or lower the temperature of the gas to lower the pressure without changing the volume. In either case, what you're going to be doing is spreading out the particles at very large distances. And at these very large distances, as we've seen, think back to Coulomb's law, at these very large distances, intermolecular forces are essentially irrelevant. So at low pressures, where the gas is very dilute, there are very few gas particles close to one another, intermolecular forces are in fact going to be very low, and we should expect ideal behavior. So the molecular level explanation is worth committing to memory. And the punchline is that at high temperatures and low pressures, gases behave ideally. We won't dive into this just yet, but different gases tend to behave more or less ideally. And that has to do with the intrinsic strength of their intermolecular forces based on their molecular structures. We'll talk about that in a future class session.